Alright, today's objective is to be able to, it's kind of pretty much that we're going to be able to use the Pythagorean Theorem in maybe unusual situations or word problems. But now they're not going to give us the triangles, they're just going to give us some values, and then we got to be able to figure out some unknown measurements based on the words that are given. And that's the objective, so it's called applications of the Pythagorean Theorem. Alright.
It asks for the diagonal.
So what is the length of the diagonal of a rectangle of side lengths 1 inch and 4 inch? So let's go ahead and draw ourselves a nice rectangle up in here. And the side lengths are 1 inch and 4 inch. It's not drawn to scale, and that's okay though. But we want to find the diagonal right here. And what makes a rectangle unique is that all 4 angles are right angles. So this one is a right angle, and from right here we should be able to just ignore the rest of this, because we only need one triangle in order to figure out what the diagonal is. And this is a right triangle, which means that if I wanted to, and you guys like this it seems like, if I wanted to make this a square, and then this one a square, and then I have this one a square, then the area of this one is 1, and the area of these is 16. So the area of this square over here is the adding of the other two, 1 plus 16. So this area is 17, and the side length is the square root of 17.
Inches.
In inches, very good. So the answer is right here.
Can you use the tick mark?
So this is a situation where we should be able to find the side lengths of a square. So it depends on squares what we're dealing with on these. So let's go ahead and draw our square. And we know from what it says right here, the diagonal length is 2 times the square root of 2. But what's unique about a square is that not only is this a right angle, but the side lengths are the same. And we don't know what they are right now, but we want to figure out what they are. So what this means is that if I took the two legs, the x's, squared those, added them, it would give me the hypotenuse, which in this case is 2 times the square root of 2, and we would square these. So let's simplify. Now this gives me 2 of these x squareds, and that would equal
8.
That's 4 times 2 now, which is 8. Very good. And now to solve for the x, we're going to divide both sides by 2, and now x squared equals 4. Then we'll go ahead and square root both of these. Square root of 4 is just 2, and that's x right here. So both of these side lengths would be 2 for the square. So 2, specifically in this case, inches. That is the side length of the square. Two ships leave a dock. The first ship travels 6 miles east and then 8 miles north and anchors for the night. So let's start that out. We'll say that we got the dock right here. And these guys are going to go 6 miles east. So that'd be 6 miles up in here. I'm looking at the, I guess what would be a compass. Northeast, southwest. Which also kind of spells the news, right? So 6 miles east and then 8 miles north. Something right here. So this would be 8 miles. And this would be ship number 1. Ship number 2, the second ship, is going to go 5 miles west. And then 12 miles south. And it will dock or anchor there for the night. This is number 2. So then it says how far are the ships from the dock. So 1 is going to be this hypotenuse. And we can solve these. Just using the Pythagorean theorem, we got 8 squared plus 6 squared equals that hypotenuse squared. So that's 64 plus 36 equals the hypotenuse squared.
Oh, 10.
So I got 100 equals the hypotenuse squared, but we just want the hypotenuse, which would be 10. In this case, it's 10 miles. So ship number 1 is 10 miles away from the dock. All right, next we want the distance from the dock to ship number 2 where they have anchored it. And right account, it says the 2 legs, we got 5 and 12. So let's go ahead and square and add these, which will be the hypotenuse squared. So I got 25 plus 144 equals the hypotenuse squared. Adding these together, 169er. And then we square root both of these, right? Just like we would have done back in count. Which gives me just C equals 13. Yep, so it appears that ship number 2 is 13 miles away from the dock. A new restaurant is putting in a wheelchair ramp. The landing the people enter the restaurant from is 2 feet higher than street level. Safety standards require that for every 1 foot of rise on the wheelchair ramp, there must be 12 feet of run. How long will the ramp have to be to meet safety standards? Round your answer to the nearest tenth. Because in real life, we don't get to put them into square roots like 2 times the square root of 7. Okay. So let's draw a picture and see if this helps us out. So the height from the road. All right, now this is 2 foot height. Right account. And it says for every 1 foot of rise, you need 12 foot of run, right? So this would be 12 foot right account, but then we need a second set of 12 feet because we have 2 feet of rise on that, okay? So starting right account, going up to the sidewalk, not to complicate things that make it go further or anything, but we're looking for the length of the ramp, which in this case is the hypotenuse. And the 2 legs, I've got this leg which is 24 feet. And this leg which is 2 feet. So I'm going to take my 2 feet and my 24 foot, square these, add them, and that will be the ramp or the hypotenuse squared. So let's go and square those. So I got 4 and 576 is C squared. So let's go ahead and add those 2 together, which would be 580. And then we're going to square root both of this. And that would give us just C. Now this it says to round to the nearest tenth, right? So let's go ahead and put it in the calculator. Alright, so I got 24.1 foot. So it was something like 24.08, yeah. But it did say to round to the nearest tenth right account. So we're going to call that good. Ray is a contractor that needs to access his client's roof in order to access whether the roof needs to be replaced. He sees that he can access a portion of the roof that is 15 feet from the ground. He has a 20-foot ladder. How far from the base of the house should Ray place the ladder so that it just hits the top of the roof? It's not really what you'd want to do because you want some space to climb up there, but that's okay. We can figure that out for Ray, and we'll round our answer to the nearest tenth. All right, to do this one, I like to draw a picture, and this is a nice looking house, right account. And we can see that the roof access that he's looking at is specifically 15 feet from the bottom to the top here. So we'll put some green grass out in here. And I got 15 foot, okay? Now we're saying that the tip of the ladder is going to touch just the tip of the roof, and it will sit here, and the ladder is 20 foot long. So we want to know how far away from the house, the base of the house, to the base of the ladder. Now this is a leg value right here, which we don't know. We'll make it A. So when we set this up, I've got A squared, and then I've got the other leg, 15, which I'm going to square. And then I've got the 20, which is the hypotenuse, which I will also square. We'll add those 2 legs, and should get the 20 out of that. So let's go ahead and square those. Bam, there we go on those. Now to solve for A squared, I'm going to need to subtract 225 from both sides. And that will give me just a squared.
Then don't you have to simplify it?
Yep. We do need to simplify these by square rooting both sides, which gives us just the a value, the square root of 175. So I got 13.2, and that is in footage. Bam. That is the distance from the base of the ladder to the base of the house. Now we got the second part up in count. B, how far should he place the ladder from the base of the house if he wants the ladder to sit 3 feet higher, which is what you usually want. Has anyone ever climbed on the roof?
Yes.
Yeah, right. You usually want some extra ladder so that you have something to hold on to.
I disagree.
If you use the ladder, yeah.
I disagree.
Alright, so let's draw a picture of these. So it's the same house. We're looking at the 15 footage right here. And then we got the yard down up in count. But now, instead of the full ladder length, we're going to sit this thing up so that we got 3 feet right here. So what's the distance from the tip of the roof? Very good, yeah, 17 foot. And we want to figure out this leg right here, which we don't know yet, but we're going to say that it's A. So it's going to set up the same way. We've got that A squared.
Could I please guess?
We've got the other leg, 15 squared. But now we need it to equal 17 squared. Alright, so 15 squared is still 225. That's great, but 17 squared, it appears, ends up being 289. So this is what we have now, and we're going to do the same thing. We're going to subtract 225 from both sides. So now we got a squared equals 64. We'll square root both of these, and that gives us a is now 8 feet. 8 feet from the base of the ladder to the base of the house. That's pretty good. Melanie is having a rectangular shaped patio built in her backyard. It is very important to Melanie that the corners of the patio are right angles for some reason. The contractor built the patio with a width of 10 foot and length of 15 foot. The diagonal measures 20 foot. Does the patio have the right angles?
Yes.
Let's go ahead and find out.
Yeah.
So, it tells us that we got a 10 foot width and a length of 15 foot, and the diagonal is a 20 foot. So, is this going to give us a right angle? That's a question mark right here. So this, by the way, is the converse of the Pythagorean Theorem. We'll see if those two legs squared will give us the 20 squared. The foot mark there is kind of slanted, so it's not supposed to look like a power of 1. But we're going to see if this is going to give us a true statement. So I'm going to do 10 squared, which is 100, 15 squared, and 20 squared. So let's go ahead and add those together. That gives us 325 equals 400.
No.
No, that is false.
No way.
So as it turns out, this contractor, thank goodness Melanie understands and knows the converse of the Pythagorean Theorem. Melanie can go to the contractor and say, "What the heck?"
No.
So we got to find the measurement from A to B on this. Apparently some spider's making some kind of webbing.
Who does that now? So yesterday.
Well, at least it's not mutated into a man that can, swing around town and save people. But in any case, let's go ahead and read through it. A spider has taken up residence in a small cardboard box which measures 2 inches, which is shown right here, 2 inches by 4 inches by 4 inches. What is the length in inches of the straight spider web? I don't know, are spider webs usually straight?
Not really.
I don't think they are, I
The
think.
spider wouldn't start in the corner of the box either.
Yeah, that'd be kind of lame, right?
It would just crawl up.
Of a straight spider web that will carry the spider from the lower right front corner of the box to the upper left back corner of the box. Well, this is a hypotenuse of some sort, which is nice. The problem is it's a hypotenuse for what would be this triangle right here, which does give us a right angle right there.
Wait, so we have hypotenuse of
Alright, now this line in purple, we already know that that's 4 inches right here.
sarcasm.
But that red line is the value that we need. Specifically, this is a right angle right here, and that is a triangle. So to find that value, what I'm going to do is I'm going to take my 4 squared, add my 2 squared, and that would give me that hypotenuse squared. So this is to figure out the value of that red line, which is part of that right triangle, which is now 3-dimensional going back into the box. So let's go ahead and square those up. So now I got 16 plus 4 equals c squared, which when I combine, I get 20 equals c squared.
It is 6.
Now when we square root these, that gives me just the length of that, which is the square root of 20. Now I could simplify that, but I'm not going to worry about that right now. I'm just going to show this as the square root of 20, because now I'm going to figure out the length of the spider web, which is part of that right triangle that with the purple and the red legs. Alright, now, so I've got those 2 legs. I've got the square root of 20, and the other leg is 4. I need to square these and add them so that I can find now the length of that spider web squared. So yeah, this ends up being 20, square root of 20 squared is 20, 4 squared is 16. And we're going to add those to make c squared. And when we do, we get 36 out of that. So now to solve these, we'll go ahead and square root both sides, which gives us c is 6 inches. So that would be the length of the spider web in this case. In the movie Despicable Me, an inflatable model of the Great Pyramid of Giza in Egypt was created by Bektor to trick people into thinking that the actual pyramid had not been stolen. When inflated, the false Great Pyramid had a square base of side length 100, and the height of one of the side triangles was 230 meters. This is also called the slant height of the pyramid, which is the volume of gas that was used to fully inflate the fake pyramid.
Are you kidding me?
So we're just going to find the volume of this thing,
Oh.
apparently. But before we do that, we need to figure out the height of this pyramid, because the formula for finding the volume of a pyramid is to take the length, the width, and the height. And so that would be like treating it like a box, but a pyramid makes it divided by 3. So we just got to figure out what the height is. We do know that the length and width are both 100 though, because it's a square pyramid there. And then when we get to it, we'll figure out what the height is. So the 230, that's the slant height, or the height of the triangle on the side, which is important for us to know because that's a right triangle that they've given us there with the cross hatching. And we do know, as it turns out, the length of this leg right here, because it's half of the 100, so that would be 50 meters right up and down. So I want to figure out the height of this thing, which is also a leg. So I've got my height, I've got the other leg, and that should equal the hypotenuse. We're going to square those, add them, and it should be the hypotenuse squared. So I've got h squared equals 2,500, plus 2,500 equals 52,900. And from right here, we'll go ahead and subtract the 2,500 from both sides. So that leaves me with h squared equals, there we go. And then to find the height, we'll take the square root of both of this, and that will give me the height. So I am going to round this to 224.5. Alright, so that is the height, which I can now replace into the equation for the volume. And the volume of that pyramid, then, I can plug that directly in my calculator, and it will give me the answer on that. Alright, so 100 times 100 times 224.5 divided by 3. Alright, this is the number that I got for the, not the height, but the volume, is 748,333. We'll just keep it at that. That's pretty big. And that also is in cubic meters.
Wait, why didn't we do the